After learning about segmentation and paging in previous modules, in this module you will see how paging hardware can be extended to support virtual memory. But what is virtual memory? We know the opposite of virtual is real. So the simple answer, virtual memory is memory which is not real. How do we turn unreal into real? Well, this is when the operating system depends on features implemented by hardware. So we see again the recurring theme. OS functionalities are possible when the hardware provides some support. Apparently, our operating system has been acting like a magician who performs tricks which give impressions to the audience that what he performs on stage is real. We saw its first trick in segmentation and paging. With the magic of instantaneous address translation by the MMU hardware, our code and data appears to be contiguous in memory. The fact is, they are contiguous in the logical memory, but in RAM, they may be scattered all over the place. The second magic trick that we'll see here is an illusion that our process is able to access memory much bigger than the available RAM on your computer. And the third magic trick is an illusion that our process is always in RAM all the time. This module will investigate how our magician does the secret tricks. Like a magician who depends on some carefully designed stage props, like his magic hat, our operating system also depends on some carefully designed MMU hardware to perform its tricks. As a side note, from now on, the term logical address space will be used interchangeably with virtual address space. Let's look for a proof of the illusion claimed in the previous page. The screenshot shows the output of a C program on a Linux machine. The logical address printed by the program shows a 12 hex address, which is equivalent to 48-bit address. So technically, the amount of logical address space accessible to this program is 2 to the power of 48, or 128 terabytes. But the amount of available RAM is only 16 meg, which is 2 to the power of 24. So that means the amount of virtual memory compared to the actual RAM size is almost 16 million times larger. Recall the analogy of demand paging we used earlier. Your printed book may have thousands of pages to read, but only 1 or 2 pages must be directly visible to us at any time. Likewise, your process may have thousands of logical pages, but only a few pages must be resident in RAM at any time. As you continue reading your book, pages will be in and out of your view. Likewise, as your process continues to run, its pages will be in or out of the RAM. So we now understand that only a small number of logical pages of a process have to be resident in the RAM. Pages that are not referenced by the execution flow of the process don't have to stay in RAM. Using a simple layout of 4 sections we used earlier, code, data, heap, and stack, on average, when a process is running, it requires only 4 logical pages, and these 4 pages must be resident in RAM. 1 page from the code section, 1 page from the data section, 1 page from the heap section, and 1 page from the stack section. Just be aware that occasionally your process may require more than 4 pages. For instance, your main function may be calling a function, but that function is at a different logical page than the main function. That means at least 2 pages from the code region must be resident in RAM. Or your program has a loop that spans across two logical pages, so both pages must reside in RAM. So what are the important ingredients to build a virtual memory? So essentially, you do need the page table and you need to implement demand paging. And of course, you need to have the physical RAM. And then finally, we need a swap disk. In earlier module, we interpret demand paging as loading pages when they are needed. But for the rest of our discussion, we have to extend the interpretation to both loading and unloading operations. These operations will be performed by an OS daemon called the pager daemon. Older operating systems may implement a slightly different daemon, a swapper daemon. The main difference between the two: a swapper daemon swaps the entire process in or out of the RAM, but a pager daemon swaps only a few pages of a process in or out of the RAM. Obviously, swapping in or out the entire process is much slower. Just for comparison, memory access time is typically around 10 to 100 nanoseconds, but disk access time is around 10 to 100 milliseconds, which is 1,000 times slower. When pages of a process are swapped out, they must be stored into a special destination, and this destination must be outside of the RAM. So this is why we need a swap disk. Unlike disk for storing user data that is usually structured into directories or subdirectories, a swap disk does not support hierarchical structure like regular user disks. Swap disks are organized into a flat structure, and consequently, I/O performed on the swap disk are faster because they don't require directory-subdirectory traversal. When discussing CPU scheduling, we mentioned three kinds of scheduler: short-term scheduler, medium-term scheduler, and long-term scheduler. Swapper or pager is part of the medium-term scheduler, and its main job is to read or write binary process image into or from the swap disk. I hope now you see some similarities between CPU scheduling and process swapping. Recall that implementation of preemptive scheduling algorithms requires a mechanism to kick out a process out of the CPU. To implement virtual memory, a swapping mechanism is needed to kick out a process out of the RAM. So, how does the swapping algorithm decide which process to kick out of the RAM? The answer to this question is found in the process state transition diagram. The objective of swapping algorithm is to free up memory space when a process needs more memory. When you're cleaning up your bookshelves or clothes drawer, the first book that you may throw away would be the book which is not currently being used. Cleaning up your RAM may follow the same algorithm. Throw away processes which are not currently running. Throughout the lifetime of a process, it will cycle through the following three states: ready, running, or blocked. That means the candidates to throw away are either processes in ready state or block state. The diagram shows only swapping out process in ready state. The state shown in yellow represents processes ready to use the CPU, and they are also resident in RAM. The state shown in light brown represents processes in ready state, but it is currently swapped out to the swap space. In the next slide, you will see why swapping processes in a block state is not a preferred option. To implement swapping, the medium-term scheduler must be designed to solve several problems. First, it must separate ready processes into two different queues. One for resident processes and another for swapped out processes. The second problem, when a process is brought back into RAM, it may have to be loaded into a physical RAM location different from the previous location it was resident. And more importantly, a process candidate to swap out should not have any pending I/O operation. Why? The I/O operation usually require data to be read from or written to either the data or heap or stack region of the process. When these regions are not currently in RAM, the I/O operation cannot complete. How do we implement demand paging? Specifically, how does the operating system load a page only when it is needed? Remember that the operating system never intercepts any memory references issued by your process. Your process will talk directly with the MMU hardware. Now remember how the copy on write is implemented. Technically, the twin process image is created on demand. The trigger of the OS to do this action is a memory write violation interrupt from the hardware. So we can borrow the same idea to implement page loading on demand. And the details of implementation requires two parts, software and hardware. The software part, the page table must now include an extra bit to indicate whether a page is resident in RAM or not. The hardware part, on logical address translation, the MMU will use this bit to trigger page fault interrupt. In the diagram, red uses 5 pages, but only 3 of them are resident in RAM. The bit in the second column encodes the residency status of each page. The 1 bit in the second column indicates that page 0, page 2, and page 3 are resident in RAM. The green process has only 2 pages loaded to RAM. Its third page is not resident. Any logical address issued by green referring to its page 2, the third page, will trigger a page fault interrupt. In response to the interrupt, the operating system will bring in page G2 into RAM. While this page is loaded into RAM, the green process will be blocked. When page G2 is completely loaded, the state of green will change again from blocked to ready, and green can resume its execution later. There are 2 important points in this diagram. First, it clearly separates what is being done in hardware versus what is being done in software. Second, it includes the role of translation look-aside buffer typically used in paging hardware. The top 2/3 of the diagram is exactly the same that you have seen earlier when we talk about paging hardware. In step 1, the page number from the incoming logical address is searched inside the TLB. In case of TLB hit, case 2A, the frame number from the TLB is used to generate the physical address, and the work of the MMU stops here. In case of a TLB miss, which is step 2B, the MMU will do a lookup into the page table of the issuing process. With demand paging, there is a chance that the targeted frame is not loaded into RAM yet. The 1 or 0 bit in the second column indicates the residency status. If the frame is resident, as shown in step 3, the frame number will be used to generate the physical address, and also at the same time, the TLB will be updated with a pair page number and frame number. And then the work of the MMU stops here. Now, if the page is not resident in RAM, shown as in step 4, the MMU hardware will trigger a page fault interrupt. And again, the work of the MMU stops here. So the next few steps will be the actions done in software. In response to the page fault interrupt, the operating system will change the state of the issuing process from running to blocked. Then the OS will run its page fault interrupt logic to find the missing page in the swap space and load that page into RAM. So this is step 5A in our diagram. Following the page load, the page fault handler will update the page table of the issuing process. The frame number will be updated and the residency bit will be updated to 1. So this is step 5B. Finally, the OS will change the state of the issuing process from blocked to ready. So the next time this process is dispatched again, the missing page is already in RAM. It is also important to understand that everything you see in the top 2/3 of the page is happening at the speed of nanoseconds, probably around 100 nanoseconds, but the actions in the bottom 1/3 of the page takes place at the speed of millisecond. When discussing process management, we mentioned the copy on write technique used to speed up fork. Essentially, copy and write is a technique to implement lazy duplication of a process image. With paging enabled, the process can have two options: either to duplicate the entire process or to duplicate only specific pages. So this diagram shows a process with 3 pages. The first page holds data, an integer. The second page is code that calls fork. The page table of the process is shown with 3 entries. First logical page at frame 24, second logical page at frame 5, and so on. Now let's say the read process issues the fork system call. In response to fork issued by read, the OS does not actually create a new process. This is why the green process is intentionally crossed out. Instead, the OS will do the following: update the process control block. Remember, the process control block is just a global table that keeps the information about all the active processes in the system. It will update the process control block by adding a new entry for the green process. And then it will allocate a new page table for green by copying the content of the red page table. And then the operating system will set the protection mode of the 3 frames to read only, which means a write attempt to any of these frames will trigger a memory access violation interrupt. At this point, both processes are essentially sharing the 3 frames. The illustration here assumes that green attempts to modify its page 0 by adding 200 to the data. But of course, this action will trigger a memory access violation interrupt because frame 24, which was associated with G0, is currently protected for read only. When the access violation interrupt is triggered, the operating system will handle by the following action. The state of green will be updated from running to blocked. Then it makes a duplicate of the shared frame, which is frame 24, and allocates a new frame in RAM to hold the duplicate, the green frame associated with G0. Let's assume that there's an open space in frame 13 to hold G0. Then The green page table is updated. The old entry 24 is now replaced with 13. And then the read-only protection is removed from both frame 13 and frame 24. And then the state of the green process is updated from blocked to ready. In order to support demand paging, the page table design must be slightly modified. We have to add a flag or bit to mark whether a particular page is resident in RAM or not. An attempt to reference a non-resident page will trigger a page fault. It should be clear that a page fault interrupt implies the process owns the page, but the page has not been loaded to RAM yet. What if a process by mistake attempts to reference a page beyond the limit of its process size? Let's say a process of size 9000 bytes attempts to fetch data or instruction at logical address 9500. When this mistake happens, the MMU should not trigger a page fault interrupt because this is an attempt to fetch a page the process does not own. To distinguish the two cases, we have to add another bit to the page table. Both page tables in the diagram have two extra columns. The VI column, or valid-invalid column, indicates whether a particular page is resident in RAM or not. The V's are associated with bit 1 and the I's are associated with bit 0. The second column, the PN column, present, not present column, indicates whether a particular page is part of the process image. The P's are associated with bit 1 and the N's are associated with bit 0. Recall that page tables are stored in the memory frames like any of your data or instructions. Let's assume a page size of 512 bytes or 2 to the power of 9. And each page table entry is 4 bytes. That means a single memory frame can hold up to 512 divided by 4, which is 128 entries. So that will be a maximum of 128 rows in our page table. However, a process of size 5K, for instance, will use only 10 rows out of 128 rows for its page table. The remaining 118 rows are not used at all. So the first 10 rows should be marked with the P flag, and the remaining 118 rows should be marked with the N flag. The illustration here assumes the maximum page table size is 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. The red process image requires only 5 pages, and that's why the first 5 rows are marked with P, and the last 3 rows are marked with N, not present. Only the first, third, and fourth pages are resident in RAM, hence the V flags. The same for the green process image. It uses only 3 pages, so the first 3 rows of its page table are marked with P flag, and the remaining 5 rows are marked with N flags.